This is the setup. What we basically do with this is we apply some normal force. Okay, this is the normal force. It's constant throughout the test. So we keep that normal force on the sample for the entire test. So this is constant. When you look at the data, you might see it fluctuate a little bit, but it's meant to be constant. The only fluctuation is just a practical control. It's just an artifact of trying to control that load. It's the computer is trying to keep that constant. It may fluctuate just slightly, but it's a constant normal load that's provided. Okay, so we put on this normal load, and that's going to induce a normal stress across the soil specimen. So this is a circular or a cylindrical specimen, so its cross section is a circle, right? So for this specimen, it has some cross-sectional area A, and its diameter is going to be provided, so you can calculate its cross-sectional area. So you have some area A. So we could calculate, based on the normal force and the cross-sectional area, we could calculate the normal stress that we are going to place on this specimen. So the normal stress, of course, is just going to be the normal force divided by the cross-sectional area, and that's going to be constant. And this is actually something that the engineer is going to specify what this normal stress is. That's going to be specified. And it's going to be consistent with the stresses that the soil will feel under the design conditions. So this is the normal stress. This is the normal stress, and this is specified by the designer. Okay, so we put on this normal stress, and when we do that, that may cause the soil to decrease in void ratio, because we may squeeze out. We may bring the particles into a closer configuration. Okay, so we call that consolidation, and that's the first phase of this test, is to apply that normal stress, allow the particles to move into a tighter configuration, and consolidate. And if there's water that's filling the voids, some of that water might get squeezed out. That's what consolidation is. Okay, so after that process of consolidation has occurred, the next thing we're going to do is we're going to start to shear the sample. Okay, so the way we're going to do that is over here, we're going to apply a shear load, a shear force, we're calling it T. So we're going to apply that shear force and move, either we're going to move the top and bottom of the box relative to one another. So we're going to push on the soil this way, and the only thing that's going to resist that movement is the soil itself, because the top and the bottom of the box are not one, they're two pieces. So we're going to push on maybe the top of the box, and the bottom may stay stationary, and we're going to, at least that's how it's set up in this figure, and we're going to actually shear right directly across this predetermined failure plane, just predetermined by the geometry of the setup. So we're going to shear this, and we're going to measure. Why we do that, we'll measure how much horizontal deflection's occurring. Okay, so another thing that we're going to measure or calculate with the measurements is the shear stress. So the shear stress is going to be that shear load T. That's going to be increasing until the sample fails, and then we calculate that shear stress by dividing again by the cross-sectional area. We're also going to measure and record the horizontal deformations. So I'm going to call that horizontal deformations. And another thing, it's not kind of clearly shown on this diagram, but we're also going to measure the change in height that occurs while we shear. Okay, so we're going to measure the horizontal deformations. This is an H for horizontal, and we're also going to measure the vertical deformations. Okay, so these two measurements we'll gather, we'll divide by the area, we'll calculate the normal stress and the shear stress. Of course, this one should be just constant. And what are we going to do with the data? So what we're going to do is create a couple of plots. So I'm going to kind of show you what these plots are. One of the plots that we're going to create is the shear stress. I'm just going to draw this here. The shear stress versus the horizontal deflection. Okay, and what that typically looks like, depending on the stiffness of the soil, we're going to see kind of an increase and then a peak, and then maybe it'll drop off to some lower value, something like that. Okay, so this represents the shear stress path versus horizontal deflection as we had a specimen in here and we sheared it and we measured those horizontal deformations. So that's what we're looking at here. And let's say this trial that we have here was performed with the normal stress. So we gathered these data when we had a normal stress being applied that was constant of, let's just say, 1 KSF. We get to specify what that is, but let's just, for this, so what we're going to do is create a couple of plots. So I'm going to kind of show you what these plots are. One of the plots that we're going to create is the shear stress. I'm just going to draw this here. The shear stress versus the horizontal deflection. Okay, and what that typically looks like, depending on the stiffness of the soil, we're going to see kind of an increase and then a peak, and then maybe it'll drop off to some lower value, something like that. Okay, so this represents the shear stress path versus horizontal deflection as we had a specimen in here and we sheared it and we measured those horizontal deformations. So that's what we're looking at here. And let's say this trial that we have here was performed with the normal stress being applied that was constant of, let's just say, 1 KSF. We get to specify what that is, but let's just, for this example, we'll say the normal stress there was 1 KSF. We're usually interested in the strength, and soil has, you can see the shear strength changes, or we had some maximum value. For what we're doing today, we're going to be interested in the peak shear strength. So this is the value that we're going to focus on in a moment. Okay, so this represents one trial of a direct shear test. The next thing that we're going to do is remove the specimen that we have in the box. So this one that's been tested, we take it out, we clean up the box, and we put another one in there. So we have another specimen. It's the same, another specimen from the same sample. So it's the same material. It's the same void ratio, same grain size distribution. It's the same, completely the same. But this time we're going to put on a different normal stress. We're going to increase the normal stress. Okay. Again, we get to choose the normal stress that we place on the specimen, and we want that these normal stresses that we choose to blanket a range of the anticipated stresses the soil will feel under the design condition. So we have a new sample. This time we're going to use a normal stress of 2 KSF, and we're going to do the same process and shear the sample. This time it might look something like this. Potentially, something like that. Okay, so this is the trial that was performed with a normal stress of 2 KSF. We have a new peak up here, and typically we perform actually 3 trials. So we take out that specimen, put another one in that's exactly the same as the others, and we shear the next one. This time we're going to get something maybe that looks like this. And this third trial is at 3 KSF. Okay, and then we have these 3 peak values. And we're saying this is the peak, so the sample has failed after the stress, the deflection increased beyond the peak. Then we see the drop off, so we're calling that failure. So we have these 3 points identified. Okay, next thing we do is we're going to make a plot in, so this is shear stress versus horizontal deflection. We're going to make a plot in shear stress versus normal stress space. So I'm going to do that right over here. So this is still, the y-axis is still going to be shear stress, and the x-axis is going to be normal stress. Just write that right up here. Okay, so from here we're interested in plotting up, well, depending on the normal stress, what was the peak shear stress the soil was able to provide us? Well, under a normal stress of 1, it was able to provide, I'll just kind of trace this over just to illustrate. It was able to provide this shear, whatever that value is, that shear strength. And under a normal stress of 2, we were over here. I'm just projecting these over. And under a normal stress of 3, we were over here. Okay, so with these trials, we've just defined a relationship between the normal stress that we apply and the shear strength that the soil provides. Okay, so what we can do is draw in what we call the failure envelope. That's what this is. This is the failure envelope. Okay, of course it is, because what it tells us is the maximum for any normal stress. It tells us what's the maximum strength or shear strength we can expect to see. We cannot, it would be impossible to have, for any normal stress, we get up to the failure envelope, the sample fails, we can't have a shear strength beyond the failure envelope, right? We can't have a value beyond the failure envelope. That's why it's the failure envelope. Okay, so it provides that relationship. So a couple of features to this. The inclination of this one we call phi, and this is what's known as the friction angle. And I put this kind of symbol up here, prime. It's because it's the effective friction angle. I'm not going to get into that too much right now, but that'll probably be covered in lecture. For now, let's just know that this is called phi. This is the friction angle. Okay. Another important parameter is the y-intercept here, and we call this one the cohesion. We give it a symbol of C. So this value right here, maybe I'll just kind of point it out. That value is C. We call that cohesion. There we go. Okay. So when I started talking about strength, I said that soil derives its strength from friction between the two particles, That's characterized by the friction angle. And if present, bonding between the particles, and I said that was called the cohesion, and that is this parameter C. And it makes sense that, as you increase the normal stress between the particles, you increase that normal stress, you're going to have more friction, right? If it's a lower normal stress, you have less kind of friction. You increase that, you have more friction, and you have more strength. And then if we go back all the way over here, let's say we have no normal stress at all, zero normal stress, but we still have some strength. Well, that must be due to bonding, so we call that the cohesion, or C. So you can characterize the strength, the shear strength of the soil. This would be a real basic equation. It would be any kind of bonding that we have C plus, so we start off here, this is our strength, and then if we then increase the normal stress, we're going to get an extra component of strength, right? We always have this C value, and then if we increase the normal stress, we have this extra component. Well, just from the geometry of that, what is that extra kind of component? That's going to be the normal stress times the tangent of the friction angle. So this is the shear strength equation, and it would be the cohesion, the normal stress, and the friction angle. So these are the two strength parameters that we aim to identify by the direct shear test, phi and C. There's one other plot that we typically make with the data, and I indicated before that we're going to gather these 4 measurements. This one stays constant, so that's constant. This applied shear load, the horizontal deformation, and the vertical deformation. So we haven't talked about the vertical deformation yet. So in addition to these 2 plots, we typically make another plot, and this one is vertical. So this is the vertical deformation versus the horizontal deformation. Let's put that over here. So this can go, this is the vertical versus the horizontal. So essentially what we're talking about is when we shear the specimen, right? We're shearing the specimen. When we do that, how is the height of the specimen changing? Is the height increasing? If that happens, we call that dilation. And if the height is decreasing, so it's actually compressing a bit, we call that contraction. So what's happening there? So we also monitor that. So it could be kind of decreasing the whole time, or it could be, and we call that contraction. Or it could, when it does dilate, it starts off and contracts slightly and then it kind of dilates up. It could be dilating. So, I mean, and it can go anywhere in between also. Okay, so I've just drawn this out. So each one of these lines would represent a trial, and we may see that particular specimen contract or maybe dilate during that trial. And I've just drawn them to the extreme, as far as extreme contraction and extreme dilation. You could have anything happening in between. And there is even a certain case where you would have no change in height at all. And so it could be anywhere in between. Generally, the denser the sample, the more likely it is to dilate. And this depends on other factors beyond just the consistency of the specimen. It also depends on the normal stress that it's being tested under. But as a general rule, looser samples are going to tend to contract more than dense samples. So you may see, if you have samples that are relatively loose to relatively dense, they still may dilate or contract, but the ones that are denser should dilate more than the other ones. So you can see anything in between. This is just an idealization. So these are the 3 plots that we're going to create. And really, the point of this test is to create this failure envelope. So that's a little bit of background about the direct shear test and interpreting the results and evaluating the strength parameters phi and c, and that will be used later for different types of stability analysis, usually with this shear strength equation. And I'll add on to this video or make another video that will discuss the details of the report, and we'll have a look at the actual data that's going to be provided. Okay, so I'm going to stop this video for now, and we'll have another one to expand on this.